This is all poppycock pseudoscience. It mucks up science. It ruins science. They use dating methods to determine the age of the strata. They date a fossil, and then they date the rock, and then they date a fossil by a rock and a rock by a fossil. There's one example of the circular reasoning of dating methods. How old is that rock? Well, let's see how old the fossil that we found near it was. Oh, okay. Well, so then this fossil is X million years old. Well, then that rock over there in the same strata, it must be the same age. It's all circular reasoning.
No, Nephi. The vast majority of radiometric dating is done on igneous rocks, not on sedimentary, not even metamorphic, and certainly not the fossils themselves. Sedimentary and metamorphic rocks are both difficult to date accurately because they are typically exposed to alteration by weathering and hydrothermal alteration in the case of sedimentary rocks, and high temperature and pressure perturbations in the case of metamorphic rocks. Igneous rocks and their minerals, by definition, are much more likely to retain their original isotopic compositions and thus provide accurate and meaningful ages. Fossils can then be dated by calculating the ages of nearby igneous material. Once a particular species of fossil has been dated, the presence of it in another rock layer can then be used to constrain the age of that particular rock. Makes sense?
Let's take, for example, uranium-lead dating. Now, when uranium decays over time, it produces lead. Okay. Now, the evolutionist finds a rock, and they date it. Let's say they find one in an upper strata. They date that rock using uranium-lead dating. And they determine that it's got X amount of lead in it. So they state, well, knowing the decay rate of uranium into lead, we can say that this rock has been here for X million years because it takes that long for that much lead to be produced by the decay of uranium. Okay? You can't know that. That's circular. That's a tremendous, unsupportable assumption.
Yes, we bloody well can know that. You seem to have absolutely no clue what an isotope actually is. Not that I'm really surprised by that. Seriously, I was taught this stuff at school when I was 15 years old. Quick crash course. Atoms with the same atomic number, that's the number of protons, but different mass numbers, that's the number of protons and neutrons added together, are called isotopes. Isotopes can either be stable or radiogenic. That is, some isotopes will decay by a number of nuclear processes to form other isotopes, which are either radiogenic or stable themselves. Lead has 4 stable isotopes useful for geochronometry, 3 of which have radioactive parents. Lead-204 is stable and does not form by decay, whereas lead-206, 207 and 208 all only form due to initial decay by isotopes of uranium or thorium. That means if we find any lead-206, 207 or 208 in a rock or mineral, we can be 100% confident that the only reason they are there is because they formed by decay as part of their particular decay series.
Lead is everywhere in the earth. There is boodles of lead in rocks in this earth. You cannot, anywhere on this planet, dig a 10-foot by 10-foot hole in the earth and not find rocks that have lead in them. It's a common element.
No, Nephi, no there isn't. You just said earlier you find lead in trace amounts in rocks. You had it right. Then you go and contradict yourself. Lead is a trace element, which is found in rocks commonly in concentrations of parts per million. For example, basalt, which is roughly the average composition of the crust, typically has lead concentrations of up to about 4 parts per million. So for every 250,000 atoms in that rock, there is 1 atom of lead. That's not very much, Nephi.
Furthermore, water washes radioisotopes out of rock. So if you find a rock at the top in an upper layer strata and it has less lead, and you find one in a lower strata and it has more lead, you know what? Chances are that some of that lead was in the upper strata and laid down and may have come out of the rocks at the top and been washed by 6,000 years of rain out of those rocks and settled into rocks below.
Oh my god, numpty. Okay, you need to also look at the word solubility then, Nev. Lead is a very insoluble element and does not wash out of rock easily at all. Uranium, however, is very soluble when it's in its 6+ covalent state, and this is one of the main sources of error in radiometric dating using the uranium-lead method. However, this is also pretty easy to avoid by dating a mineral called zircon. Zircon is an accessory phase in rocks such as granite or rhyolite and is exceptionally useful for 3 reasons. Firstly, it is very, very tough. I should know, last year I spent some time separating zircons from rhyolitic lava by dissolving the rock in industrial-strength hydrofluoric acid. The only thing that didn't dissolve was the zircon, and this stuff will dissolve glass in a matter of minutes. What chance do you think water has? Secondly, it has very low diffusion rates. This means that atoms that make up the mineral are essentially locked in place and are very difficult to move. Under exceptional circumstances, such as prolonged thermal metamorphism, the atoms may diffuse out of the mineral, but this is not only well understood, but is also easily corrected for, and I'll explain how in a later video. Lastly, due to the structure of the crystal lattice, zircon willingly lets uranium into its structure, but not lead. This is because uranium is typically in its 4+ covalent state, the same as zirconium and silicon, so easily substitutes for them. Lead, however, is typically in its 2+ covalent state and has a very large atomic radius, which means it struggles to fit into the zircon structure. This means that essentially all the lead you find in zircon comes from the decay of uranium. Zircons are nature's tiny geochemical stopwatches, are invaluable for unravelling the ancient history of the Earth.
I assume that makes it science.